So now we're going to look at applications of aqueous equilibria. Solutions of acids and bases that contain a common ion are what we're going to look at now. So common ion, what do we mean by common ion? Okay, well we mean basically a ion that is generated in solution that is common to both your weak acid as well as the salt that you are adding into the solution. This could also work for a weak base and a salt that has a common ion in that respect. So HA and NaA, these two generic weak acids and salt, both have a common ion, which is this A- ion. So a real example of a weak acid and a salt that have a common ion are HF and sodium fluoride. So hydrofluoric acid and sodium fluoride both have the common ion. When sodium fluoride is put into solution, because it's a strong electrolyte, it ionizes completely into Na plus and F minus. Okay, and HF is a weak acid, so it ionizes partially into H plus and F minus. Notice that they both have F minus as the common ion. Okay, so the major things that you're going to find in solution are going to be HF, Na plus, F minus, and of course, obviously, water. Now notice we didn't include H plus in the major species because of the fact that we know that HF is a weak acid and it only slightly dissociates. So basically, when we have a common ion added to a solution that has a weak acid or a weak base, that's actually going to affect features of the specific solution. Okay, so how does it affect the equilibrium of the solution? So if we look at the ionization process of HF, which is hydrofluoric acid, we know that HF is going to ionize slightly into H plus and F minus. Okay, now if I add sodium fluoride to the solution, that's the equivalent of adding additional F minus to solution. And we know from Le Chatelier's principle that if we add more of a product, that we're going to shift our equilibrium towards the reactants, or to the left. Okay, so what that means is that by adding this common ion, this common fluoride ion, we actually shift the equilibrium back towards the reactants and subsequently decrease the dissociation process or percentage with respect to the acid. So what's going to happen is that with less dissociation, you're going to have less H plus in solution. Less H plus means that your pH is going to increase and subsequently your solution is going to become more basic. Okay, so a solution that has both NaF and HF, because they have a common ion between them, is going to be less acidic or have a higher pH than a solution that just has HF on its own. Okay, so as I said, this same idea or concept also applies to bases, weak bases in solution. Okay, so if I add ammonium chloride to an ammonia solution, we're going to see this common ion effect come to fruition. Okay, so NH4Cl is a salt. It's ammonium ion and chloride ion. When it ionizes completely, it ionizes into NH4 plus and a chloride ion. And basically, what you should be able to glean from this is that when I add NH4Cl to a solution, I'm actually adding NH4 plus and Cl minus ions into the solution. Now, ammonia, we know that it's going to react with H2O and produce NH4 plus and hydroxide ions in solutions. And we know that this is the normal ionization process that occurs for this base. So if we look at the products associated with this base as well as the products associated with the salt, you notice that we have the common ion ammonium in both of these. Okay, so if I have an NH3 solution, okay, I'm going to have these ionization products to some small degree, right? But by adding this salt, this NH4Cl, what I'm doing is I'm increasing the amount of NH4 plus. By increasing the amount of NH4 plus, I shift the equilibrium towards reactants and subsequently decrease the ionization process that's going to occur with this base. So in turn, that reduces the amount of hydroxide that's in solution. And if I decrease the amount of hydroxide, that's going to end up increasing my pOH or decreasing my pH, however you want to look at it. And that's subsequently going to make the solution less basic than it normally would because I'm going to have less hydroxide in solution. Okay, so whether this is a weak acid and a salt with a common ion or a weak base with a salt that has a common ion, the effects are going to be similar in terms of the shift and how it affects the ionization of that acid or base. So basically, the common ion effect is when you add an ion that's already involved in the equilibrium expression, and that ion's addition subsequently affects the overall equilibrium position. Okay, so the presence of common ions are going to suppress the ionization of weak acids and bases. Okay, so it's basically going to shift that left towards the reactants. And subsequently is going to make your weak acid solution less acidic and your weak base solution less basic, because you're putting less H plus in solution and less OH minus in solution, respectively. So how's this common ion effect going to affect our equilibrium calculations? Well, let's go ahead and let's look at some examples. Well, in this problem, they've told us to calculate our H plus concentration and our percent dissociation of HF in a solution that has 1 molar concentration of HF and 1 molar concentration of sodium fluoride. Now, we know that HF is going to slightly ionize into H plus and F minus. Remember, it's a weak acid, okay, as indicated here by the Ka value. So we know that we're going to have that process occurring, and we know that sodium fluoride is a strong electrolyte, so it's going to break up into sodium and fluoride ion. Now, the major species that we're going to obviously be looking at are HF, F minus, okay, but notice that we're going to pretty much ignore H2O because it's not involved in equilibrium expression, and we also know that our H plus is present in very, very small quantities. Okay, so most of the things that we have in solution are going to be interrelated with each other, hence the HF and F minus, that common ion species being shared between the two. Okay, so how does this look when we actually go to do our equilibrium calculations? Well, if we look at our equilibrium expression for the ionization of hydrofluoric acid, we know that we're going to have H plus O times F minus all over HF's concentration, okay, and we know that our equilibrium constant is 7.2 times 10 to the negative 4. I'm going to set up my ice table just like I normally would when I'm solving for X, because, you know, obviously we're solving for that H plus. Okay, but notice, when we enter our initial values, notice that we have our concentration of HF and we have our concentration of F minus. Okay, so basically initially we have both reactants and products present in the solution. Now, of course, these are going to equilibrate so that they have the appropriate concentrations at equilibrium. So we set up our ice table. Obviously, the changes are going to be the same, and our equilibrium equilibrium concentrations are going to look like the following. Now, we know we're going to plug these values into our equilibrium expression up here. Okay, so we've gone ahead and plugged in our concentrations at equilibrium into our equilibrium expression. Okay, as you can see here. Now notice I'm assuming that the change in the concentration of my F minus and HF is going to be relatively small with respect to X. I'm going to make that assumption. Okay, so I'm going to drop off the X values here and subsequently end up with this equilibrium expression that's equal to 7.2 times 10 to the negative 4. I'm going to cross multiply up this 1, okay, and then divide out by 1. Okay, so the concentration of my H plus, or my X value, is going to be 7.2 times 10 to the negative 4. If I check that value, I know that my 7.2 times 10 to the negative 4 is a whole lot smaller than 1% of the original concentration of HF, so I don't need to worry about the approximations that I made. I don't have to go back and do the quadratic equation. Okay, now they've asked us to solve for H plus, okay, and they've also asked us to solve for our percent dissociation. Okay, remember our percent dissociation is our H plus concentration divided by the initial concentration of our HA times 100. Okay, so I've subsequently plugged those in here and got 0.072% dissociation. Okay, and the pH of this solution, if I just take the negative log of my H plus, is 3.14. Okay, so basically the percent dissociation when I have the common ion F minus coming from the sodium fluoride in the same solution container we end up with a very small percentage of H plus ionization. Now let's go ahead and let's compare this to the values of a solution containing only 1.4 molar HF. So there's no sodium fluoride, there's no common ion effect in this situation seen here. So when we go ahead and do those calculations, okay, notice our H plus concentration is several orders of magnitude larger than when I have the common ion situation. The pH is also much lower. That means that I've been able to put more H plus into solution, subsequently lowering the pH. And my percent ionization, or the percent dissociation, is also quite a bit higher when there isn't that common ion present. Okay, so remember the common ion effect is basically taking advantage of the whole equilibrium rearrangement in Le Chatelier's principle. So by adding more of this common ion, basically I'm adding more of a product, I shift my equilibrium back in the other direction, and subsequently lower the percent dissociation or percent ionization, lower the percentage of H plus in solution, and of course make my solution a lot more basic than it normally would be had more H plus been allowed to ionize.